measure integration and analysis class. And today we'll continue with the outer measure of closed bounded interval. So in our previous video, we have checked the outer measure for some open interval. So we are able to check some good properties of outer measure. Likewise, the countable subadditivity of outer measure. Okay, so one more good property of outer measure that we should prove is that if A is less than B, then the outer measure of the closed interval A comma B should be B minus A. So this is what we are going to prove in this video. Okay, so what means that the outer measure of B, A comma B should be equals to B minus A. So let's first of all prove fixed direction. Proof if x_n is greater than 0, then A minus x_n, B plus x_n, empty set that is a sequence of open interval intervals whose union contains the closed interval A comma B. Alright, so if that be the case, thus the outer interval of this guy would be less than the length of this guy, which should be B plus x_n minus A plus x_n, and that should give us B minus A plus 2x_n, and then 6s, since x_n is an arbitrary number. It's an arbitrary number that implies that the outer measure is less than or equals to B minus A. So this direction is very easy and a nice one, but to prove the other direction, that is not quite easy. So there are some basic definition and some theorems we need before we can able to prove that the outer measure of A comma B is greater than or equals to B minus A. So if we are able to prove this, then this will now imply that the outer measure of a closed interval is equals to the length of that interval, which will be a nice properties for outer measure to satisfy. So in order to prove this, we have to check some basic definition, then we come back to that. Take note of this. We'll come back to this after some basic definition. So the first definition we need is open cover and then finite subcover. So suppose A is a subset of R. A is a set and can be an arbitrary set. Okay, so a collection fancy C of open subset of R is called an open cover of A if A is contained in the union of those guys of all the sets in C, in the fancy C. So take note of this. This guy is called an open cover of A if A is contained in the union of those guys. So with that also we say that an open cover C of A is said to have a finite cover okay, so a finite subcover if A is contained in the union of some finite list of set C. So take note of this definition. So in other words, so we say an open cover G is said to have a finite subcover if we can just cover our set A with finite list of sets in the fancy C. Otherwise, the open cover does not have a finite subcover. So let's give some example. Look at this, the collection K. So K, comma K plus 2 shows that K is positive integer. So there is an open cover of 2, 5, which is a closed interval. Why? Because this our closed interval is contained in the union of K, K plus 2. And also you will notice that we don't need infinite cover of this guy. We already just need some finite cover of this guy. So we say that this open cover has a finite subcover. And then the reason is that this 2, 5 is already a subset of 1, 3 union 2, 4 union 3, 5 and then union 4,6, and this is a finite subcover, so we don't need infinite cover in order to cover our closed interval. So that is one example of open cover that has a finite subcover. But let's check another example. Example 2. So we have another collection which is an open interval k comma k plus 2. Okay, k positive integer. So is an open cover of 2 comma infinity. Why? Because this is subset of the union of our collection k comma k plus 2, k equals to 1 to infinity. However, this open cover does not have a finite cover because this our function is not bounded here. Okay, this open cover does not have a finite subcover because there exists because they do not exist finitely many sets of the form k plus 2 whose union contains 2 comma infinity. Okay, so let's take another example 3. Okay, for the third example, we have the collection f0 2 minus 1 over k. So we such that k is a positive integer. So it's an open cover of 1,2 because it contains in the union of all these guys 2 minus 1 over k equals to 1 to infinity. So, but this open cover does not have a finite subcover. So because they do not exist finite many set of the form 0,2 minus 1 over k whose union contains 1,2. Then that's the major theorem we need in order to prove the other direction of the outer measure of closed interval. Is this wonderful theorem that we are going to check now, and that is called Borel theorem. So the theorem says every open cover of a closed bounded interval, so of a closed bounded subset of R as a finite subcover. So as you can see in one of the example, the first example we did, which is this. So this is a closed bounded subset of R, then open cover as a finite subcover. So you want to make it more, you want to generalize it, and that is the theorem of Borel. So we have to prove this, then we can now use it to prove the other direction of the outer measure of our closed bounded subset of R. So first, suppose F is a closed bounded subset of R, and then we have C to be an open cover of F. So we want to prove that this open cover has a finite subcover. So first, let's consider the case where F equals to A comma B for some A comma B belongs to R with A less than B. So then, if that should be the case, thus we see that C is an open cover of A comma B. Alright, so because we are already divided, suppose F is closed bounded subset of R and C is an open cover of F. Is F equals to this, then C is an open cover of A comma B. So we want to now see a way whereby we can construct a finite subcover and extend it to all the entire set. So let D be equals to set D such that A comma D has a finite subcover from C. This is right there. Assume that this is our A comma B. Okay, so we tried to get a set here. We tried to define our D to be a set D in around here, whereby this set H to D has a finite subcover. So we have a finite subcover to this point. Okay, so then we can now extend it. If this have a finite subcover, then we can, since our subcover is an open set, Then we can find a small delta whereby we can stretch it, and as we continue to stretch it, we can find a finite subcover that will cover the entire of A, comma B. So if we have that D to be that, so you will note that A is an element of D, just as what we are divided. If D is here, then you know that at least there's a finite subcover that is going to cover from here to here, so it will also include A. Why? Because A belongs to G, which is for some G that belongs to our collection of sets. Thus that means D is not empty set. So if D is not empty set, then we should be able to have a sup of D. So we say let X equals to the sup of D, which is the lowest and greatest upper bound. Okay, so if that should be the case, so if X is in D, that means that X also should belong to the entire of, should be an element of A and B. Hence, let's say there exists an open set G that belongs to C such that S belongs to G. So for that open set of G, we can find a small delta such that S minus delta, S plus delta is still a subset of G, because that's the definition of an open set. So because X is equal to sup of D, that means that there exists a D that belongs to this element S minus delta, comma X. Since S, we assume S to be sup, so there must exist a D that belongs to this element. And then for positive integer G, there must be a finite collection of open interval G1, G2, Gn that belongs to our collection, such that A, D is a subset of those guys. So what we just did now is that we have our D, A, B, then we have this somewhere here. Okay, so we are able to find a finite collection of open interval whereby we are able to cover these points. So but since our open cover is an open set, we can also extend it to be able to cover the entire of A, B. So the trick is that now A, D prime is a subset of G. So we include G, another subcover, such that it's going to cover another point, maybe down here. So G, G1, Gn for all D prime that belongs to S, delta. So this to the right point of our X. Okay. So thus D prime belongs to D for or D prime that belong to S comma S plus delta intersect A comma B. So that means that our S cannot be the soup, and this implies that our X is equals to B. Okay, and then this show with D prime equals to B. So this shows that A comma B has a finite subcover from C. So completing the proof for that first case. In the case where F is equal to A comma B. So let us check an arbitrary case now. So now suppose F is arbitrary closed bounded set subset of R, and that C is an open cover of F. So let A comma B belongs to R be such that F is inside of A comma B. F is a subset of this guy. So now we can construct a open interval U C union R, take away F, and this is an open cover of R. Okay, and hence if it cover R, obviously it should also cover A comma B, right? So, and then by our first case, we are able to see that there exists G1 dot Gn that belong to called C such that A comma B is a subset of those guys G1 dot union dot union Gn union I'll take away F. So that means that F, which is a subset, our F can be a subset of G1 union dot union Gn. So since we don't need to cover AB, we only need the subcover that only cover F, and that completes our proof. So in other words, if there exists a closed bounded subset of R, then an open cover of a closed bounded set of R has a finite subcover. So with that now, then we can now go and prove the other direction. So that leads us to this outer measure. closed interval. So suppose a comma b belongs to R with a less than b, then the outer measure of a closed interval should be equals to b minus a. Okay, so we have already proved that the outer measure of a comma b is less than b minus a. So we just want to prove the other side now. Okay, so to prove the inequality in the other direction, so suppose I1, I2 dot is a sequence of open intervals such that a comma b is a subset of these guys. Okay, so by the theorem we just proved, by the Heine Borel theorem, so another there exists a finite subcover such that a comma b is a subset of I in I2 dot union dot in I n. Okay, so we now prove by induction on n that the inclusion above implies that the summation of those lengths of ik is greater than or equals to b minus a, which is actually our goal in order to prove the other direction. Once we are able to do that, then we are done with the proof. So let's check for the base case. For the base case, when n equals to 1. So if there's only one interval, interval I, which is c comma d, then a comma b should be a subset of that interval, and clearly c should be less than or equals to a, and then b should be less than or equals to d. So the length of I1 should be equals to d minus c, and since d minus c is greater than b minus a, so does the claim holds? For n equals to 1. So this is just what it did. We have a comma b, and we have one interval which we can say that it is here. We have our c here, and then we have our d here. So definitely the length of this CD will be greater than the length of this AB. So that is just for base case. So let's go to the inductive step. Inductive step, such that n is greater than 1. So in order to do this, we have to assume that the claim holds. Claim holds for n. So suppose for n intervals I1 dot IN, so the total length satisfies this summation k equals to 1 to n length of ik greater than c minus a. This for some c that belongs to a comma b. Okay, so let's add one more interval. Add one more interval in plus 1. So suppose we now add one more interval, let's call that one n plus 1, which is equal to c comma d, where c is less than b. Then you have what? Then a comma b will be a subset of the union of these guys. So then we can now split the interval. Since a comma b is a subset of union this is dot in union in plus 1, so the part a comma c is covered by the first I at the end, and then the part CB is covered by 1n plus 1. So let's apply the induction hypothesis to AC. So by induction, hypothesis, the total length of I1 to IN, so we have it to be summation k equals to 1 to n, length of ik is greater than or equals to c minus a. So we have this here, we have this here. So now wants to add the length of IN plus 1, the length of in plus 1, that is equals to c comma d is length in plus 1 equals to d minus c. So adding this, we have k equals to 1 to n plus 1, length of ik is equals to summation k equals to 1 to n, length of ik plus d minus c plus length of n plus 1, which is equals to greater than c minus a plus d minus c. Okay, if we simplify this, then you have k equals to 1 to n plus 1, let 1k to be greater than b, so it will be greater than d minus a, and since we have b to be less than or equals to d, okay, so since b is less than or equals to d, so then that k equals to 1 n plus 1, length of ik will be greater than b minus 1. So this is what we did. We have a to d, then we have a to c. Okay, so our i's 1 to in covers from this point, so that is what I1 dot in cover, or our in plus 1, in plus 1 cover this point. You see that? So you see that from this to a, our b somewhere here. So you see that from a to d is actually greater than from a to b. So and that's complete. So taking as the limit n tends to infinity, I was taking the infimum, taking the limit n tends to infinity, so summation k equals to 1 to infinity will still be greater than or equals to b minus a. So we combine this together, we have the length of a closed bounded interval to be b minus a, and that completes our proof. It's actually a nice proof, but kind of rigorous. Okay, so another theorem which is kind of trivial is, let's see, we have nontrivial intervals are uncountable. So that is every interval in R that contains at least two distinct elements is uncountable. So we can just easily prove this. Proof: suppose I is an interval that contains a comma b to R with a less than b, then since I is an open interval that contains a comma b and then measure preserve orders. Then we have this to be greater than b, the length of a comma b, and that is equals to b minus a, which is actually greater than 0. So this follow by measure preserve orders. So after measure preserve order, okay, and this actually come from what we just proved now from previous proof, and then that is satisfied. But one of the theorem that I'm going to end this video with is that nonadditivity of outer measure, that is, even though we have a disjoint subset A and B, of R such that the size of A union B is not equal to the size of individual. So this is one of the deficiency of outer measure, in which we are going to address by constructing by looking into another type of measure which actually satisfies this non-additivity of outer measure, because we need these properties to be able to get a proper integration for our functions of our arbitrary set. So because of these properties, so we are going to move to another session whereby we're able to divide another nice measure which we can begin to use except this outer measure. So here we are going to stop for section 2a, and then in the next video we will try to check solutions to some exercises for section 2a. Hope to see you in the next video. Thanks.